Swayam Prabha. Digital India. Educated India.
Welcome back, students. Just to give you a feel for our classroom, I'm sitting in one of the Girish Gaitonde lecture halls, and generally we do the lectures over here. So I thought I will show you how the classroom looks like over here in your absence. So in this course, we started off with a PN junction. I went through some device physics analysis, and then modeling of the PN junction, and then some circuits using PN junction diodes. Then we did bipolar junction transistor. We did some device physics again, and then large signal, small signal model, and a few circuits using the bipolar junction transistor. In today's lecture, we are going to talk about MOS devices, or metal oxide semiconductor field effect transistors, MOSFETs. Whatever we are seeing around us today, the huge development in electronics area has happened mainly because of MOSFETs. We are going to talk about why they are so important. But the first thing is, in 1960s, MOSFETs were invented in Bell Labs by Kang and Attala. So as I had described to you earlier, BJTs had a long run of almost 25 years in the semiconductor space. And main thing they did was to replace the bulky vacuum tubes. BJTs led the miniaturization of electronic circuits and systems, and there came along MOSFET transistors, which completely replaced the bipolar junction transistors everywhere. We are going to see why that happened and why MOSFETs ruled for so many years and still going strong. BJTs are still useful in ultra high frequency range where they have the best performance even compared to MOSFETs. In this lecture, we're going to talk about MOSFET devices. MOSFET is metal oxide semiconductor field effect transistors. We'll start with a cross section and try to gain intuitive understanding about how the device works. So this is the basic cross section of the device. We'll start from this and we'll build our understanding based on this. We start with a P-type of semiconductor. It's a lightly doped P-type of semiconductor. On top of that, we have this yellow oxide region, and magenta is the metal. So this is the metal and this is oxide, and the bottom one below is a semiconductor. Now if we apply potential Vx plus minus in this fashion, let's analyze what will happen. So we are making the metal positive compared to the P-type of semiconductor. So P-type of semiconductor is doped with acceptors. So for example, in this case it would be boron, and it would have abundant holes, and it would have electrons, free electrons as a minority carriers. So as soon as you apply potential in this way, what we would see then is you would see positive, the metal getting positively charged plus this way. I'm just showing it outside. Since we are applying a negative potential to the P-type of semiconductor, then all the holes which are positively charged, they will repel away from this interface just below the oxide region, and the holes will start going towards this negative terminal. In other words, you can understand that the electrons, free electrons coming from the battery, they will enter the P-type of semiconductor and they will fill in all the hole region. So since the holes have left the P-type of semiconductors, we are left with negatively charged ions. Okay, since the holes have left the P-type of semiconductor because they got repelled by these positive potential on the metal side, negatively charged ions which are exposed in the P-type of semiconductor. Now if we continue increasing Vx further, then what will happen is the free electrons which are in the P-type of semiconductor, which are the minority carriers, they will start coming towards the interface region, and you will see these free electrons which are coming close to the interface. So far, by increasing Vx, we are able to get the minority carriers in the p-type of semiconductor, which are electrons, at the interface region just below the oxide. Now, let's do something even more interesting. We will apply a potential Vy in this fashion. We are applying positive potential to the left side and negative potential to the right side. Naturally, as we keep increasing our Vx further, then negatively charged electrons will come under the channel. They will start coming from this negative potential of Vy. So we are drawing more free electrons from the battery Vy under the channel. With increasing Vy, the left side being positive and right side being negative, what we would see is that the electrons are being drawn from negative terminal of the Vy. They will go under the channel and they would flow towards the left side. Since the electrons are being drawn from the right side, this region is called source region because this is the source of electrons, and left side is called drain region because that's where all these electrons, the free carriers, are being drained. The p-type of semiconductor we started with is called substrate or sub-region. Electrons are flowing from source to drain, as a result of which the current will flow from drain to source. So the flow of the current, which will be in this fashion, I, and this is called IDS. So when we increase the gate voltage Vx, if we keep increasing it beyond sufficient positive value, which we call that VTH, threshold voltage, mobile electrons flow from source region and form channel under the gate. So originally we started with a p-type of semiconductor which has holes, which are positively charged carriers, and by applying Vx potential we shooed away the holes from the interface region, and if we keep increasing Vx further, then after critical value of voltage, which is VTH, we call that threshold voltage, we withdraw free electrons from the source region and they form a channel under the oxide region, and that's when we call it, the channel is inverted, or we call that inversion region, because the carriers, the free carriers which were holes before, now they are electrons, so it's called inversion region. Let's talk about the threshold voltage VTH. The threshold voltage VTH is given by this expression. Threshold voltage is given by 5 ms, which is 5 ms is the work function difference between gate and the substrate, the p-type of substrate. 5F is the surface potential. 5F is given by this equation, KT over Q. This you're familiar with, which is our VT in the bipolar case, ln of N sub divided by Ni. N sub is the doping density in the substrate. In this case, it would be Na. Ni is the density in undoped silicon, carrier density in undoped silicon. So what this is telling us is, if I increase my N sub, or in this particular case, if I increase the doping concentration of the p-type of semiconductor, then I will need more and more potential Vx to shoo away the holes from the interface. Okay, so this kind of makes sense. So Vt will increase if I increase N sub. Q depth is the charge in the depletion region, and that is given by this particular expression, 4Q epsilon Si 5F times N sub, and square root of that. Epsilon Si is the dielectric constant of silicon, and that is given by, that is 11.68. Cox is the gate oxide capacitance. So another insight is, if we reduce the thickness of the oxide region, then we expect the capacitance Cox to increase. Another way to think about it is that if you reduce the thickness of the oxide, then gate would have more and more. The gate would have stronger influence on the channel, and even at a lower VTH value or a lower Vx value, you would have inverted the channel. Holes in the p-type semiconductor, they would run away from the interface, they would get repelled from the interface, and it would be easier for us to get an inversion layer under the channel. So reducing thickness of the oxide region, by which we would increase the Cox, would result in reduction in VTH. Increasing substrate doping also would increase N sub, and that would also increase our 5F here, and as a result of which the depletion region charge will also go up, which will also increase our threshold voltage. So that's the intuitive explanation for the threshold voltage of the device. Next, we will look at MOSFET from the top view. We call that view as a layout view, and this is what you would do in the EDA tools to draw the device. Let me explain how this represents a MOSFET device. The green region in this particular case is, this region is a diffusion. In this particular case, it would be the N plus diffusion that we are doing in a P type of substrate. So these two are our N plus diffusion layers. The yellow region is a P plus diffusion, and the magenta, which is in between over here, that is the gate region. So if I am drawing a MOSFET transistor in our layout tool, CAD tool, then this is the way the top view will look like. Now this may look a little bit funny to you, but let me take a cross section of this device and it would become obvious. The blue region is the metal contact to the diffusion regions. So what we are going to do now is take a cross section, and the cross section will be taken right here in this region like this. Once I show you the cross section, it will be very clear to you what the device looks like. Now let me explain the cross section for you. As I said again, the green region is an N plus doped region over here. Similarly, here is another N plus region, and we started off with a P minus substrate. If you remember the first lecture in which I have shown you a silicon wafer, that's what we call P type of substrate. We start off with a silicon wafer, which is a P type of silicon wafer, and then we will start doing the doping in that silicon wafer. The yellow region here is P plus doping, okay, and the magenta region is showing the metallization. The white region is actually oxide. So we can call the left part, the left connection N plus region is a drain, the right part we call it as a source, and the middle part is obviously the gate. So the magenta part is metal, and obviously you can see metal oxide semiconductor in this vertical fashion right here. Right here, if you look at it this way, then it's a metal oxide and semiconductor, and that's why we call it a MOSFET. So this is the way the cross section of this particular device, we call it as NMOS device, looks like. Let me draw a 3D view of this device and things will get even clearer. In the 3D view, I'm not going to draw these metallizations for drain and source. Oh, by the way, I forgot about one thing, which is this last yellow region, which is P plus region. P plus region will connect very well with the P minus substrate, and it's called body or substrate connection. It's often labeled as B. So this is a 4-terminal device: drain, source, gate, and bulk or body, which is B. Now I will draw 3D view of the MOSFET. It would be great if you can draw these pictures yourself to make yourself comfortable, because as an electrical engineer, you should know how the cross section of the MOSFET looks like. And once you can visualize it, it will be very easy for you to understand the transistor action. So let me explain the 3D view to you. The left green part is N plus region here. The right green part is another N plus region. This we can call it as a drain, and this would be your source. Right side would be your source. Yellow region is an oxide region, and magenta is a metal. Few things to note here is, if we look at the source and drain regions, then we would have a diode right here. Since this is a P substrate, you would have N plus P diode at the drain region, and similarly you will have N plus P diode at the source region. In this particular case, let's draw all the features. This would be your T-ox, oxide thickness. One important feature of this transistor is length of the channel. The channel is formed in this region, and this is called length of the channel, or L, and the lateral dimension, or the one that's going in the screen, is called the width of the channel. So this region is called width. The T-ox, which is oxide thickness, can be of the order of 10 angstroms to 20 angstroms. Angstrom is 10 to the power minus 10 meters. You must have heard different numbers like 28 nanometers, 65 nanometers, 90 nanometer technology. This L is what is being described over there. So if L gets shorter and shorter, then we can pack more and more devices on a chip. And if you remember in the first lecture when I told you the story, when I was working on my own, building my own devices, we had 5 micron technology in IIT Bombay at that time. And now we are talking about 5 nanometers. So that's 3 orders of magnitude of change in the device sizes that we have seen. So we can immediately see that you can pack more and more devices in the same area, and that's what has made miniaturization as well as packing more and more functionality on a chip by adding more and more transistors on a chip is possible. So this channel length L we are talking about is referring to 28 nanometers, 65 nanometers, or 90 nanometer technology. Another thing I have to tell you is, so in the initial days of MOSFETs, we started off with metal as the gate material. And one of the issues with metals is you would deposit these drain and source region, and then you would grow the oxide, and then you would put metal on top. The metal deposition step or the feature defining stage for metal was independent of the drain and source region defining step. As a result of which, you will have sometimes you can have metal is not overlaying completely on the source or drain regions, and then you will have a transistor that doesn't work. So to prevent that, you would have to have a large amount of overlap between metal region and the drain and source region. So that was one problem. As more and more research was carried out, they figured out a way to deposit silicon itself. Instead of metal, we would use polysilicon. And polysilicon is a semiconductor by itself, but then you can dope it heavily and it will start acting like a metal. So this had 3 advantages. One is the polysilicon is used to align the source and drain region. And let me explain what that means to you. Again, this is not really, this is more getting into the devices, but it's an interesting understanding of how the transistor is drawn. What you would do then, you would pretty much draw the oxide region first, and then you would draw on top of that you would have the polysilicon. So this hashed region is a polysilicon, and then you would use polysilicon region as a mask for the diffusion. So after depositing polysilicon, after getting this feature, then if you do doping of phosphorus in this fashion, then you would get the phosphorus would get in this region like this, and phosphorus will get into the polysilicon, which is here, and polysilicon will become, because we are doping it with phosphorus, it will start acting like a metal because it has a lot of free electrons over there. Okay, and these are our doping regions which are for source and drain. So polysilicon and oxide acts as a layer to carve out our source and drain region, as a result of which this process is called self-aligning process. So once again, let me explain. Earlier we used to use metal. However, metal was deposited separately and the metal would move around, so you have to leave out a lot of clearance in the size of the device. Whereas when you use polysilicon, the polysilicon gets doped by the source and drain region impurities and it becomes like a metal, as well as it acts as a mask for defining source and drain region. So this was an advantage with the polysilicon gate. The second advantage with polysilicon is the diffusion process is a high temperature process. So polysilicon can withstand that. However, metal cannot withstand that. As a result of which, you have to do the diffusion part first, and then you had to do metallization part separately later on. The third advantage of using polysilicon is by doping, by controlling the doping of polysilicon, we could change this 5MS, which is metal to semiconductor work function. So this gives you adjustment in VTH of the device. So you can engineer the device with finely controlled threshold voltage with polysilicon. So what I'm trying to tell you is we started off with a metal oxide semiconductor, but in reality, instead of metal, we use polysilicon, which is heavily doped to act like a metal. Okay, so This is a subtle point you should know. Now let's start with characterization of this device that we have just looked at in 3 dimension. So first I'm going to draw the cross section of the device again, and please draw it yourself so that you are familiar with it. This is something that you should definitely know. So I'm going to apply voltages to this device. What we will do is we will apply ground potential to our P substrate, P minus substrate, by connecting to this P plus region. The P plus region that we have drawn here provides a very good connection to the P minus substrate. The source region also we will connect it to ground. So this is our bulk, this is our source, and we will apply a VDS. This is the drain region. We are going to apply VD like this. And to the gate region, we will apply a gate potential in this fashion, plus. I'm going to draw this in the transistor format on the right side. So the symbol of the NMOS is this way. I'm drawing the device in a horizontal manner, but that's okay. And source is our ground reference. We are connecting plus minus VDS, and we are connecting plus minus VGS. Now we will draw the transfer characteristics or IV characteristics of the device based on what we know so far. So what do we know so far? Let's draw axis here first and understand what axis I'm talking about. So on the x-axis I have VGS. On the y-axis I have IDS. So when VGS is 0 in this particular case, there is no channel formed, there is no inversion layer formed in this particular device. So we will have 0 current, IDS. There is no current flowing from drain to source. When VGS is equal to VTH, we are just beginning to form the channel under the device, and this would be our VTH right here. And as soon as we increase the voltage VGS beyond VTH, we expect some curve. We don't know what that's going to look like, but we will draw it for now like this, and we will try to figure out what this curve looks like. So this is the way the transfer characteristics will look like. We don't know how this curve is going to look like yet, but what we expect is IDS will be 0 for VGS less than VTH, and there we call it the transistor is turned off. And if the VGS is greater than VTH, then there is inversion layer. What does inversion layer? Reminder again is if it's a P type of substrate, then there are negatively charged electrons which are available under the channel to carry the current, and that's what we call as an inversion layer. We started off with holes in the P type of substrate. Now we have electrons in the P type of substrate. So that's why we call it inversion layer formed under the channel. Now let's draw a different characteristics. Here I'm going to show IDS on the y-axis, and I'm going to show VDS on the x-axis. Let's say we started off with 2 different points on this curve. So this represents 2 different VGSs, VGS1 and VGS2. What we expect is for VGS1 greater than VT, there will be some current that will flow from drain to source, and that current would look like this. Let's say something like this, because as you increase VDS, you expect the current to increase in the channel, and this would be for VGS1. For higher VGS, let's call this VGS1 and VGS2, we expect higher current to flow. This is again a very high level simplistic understanding of the device is going to behave. We are going to dig in a little bit of device physics to understand how these curves are going to look like and different regions of operation of the device. Now I'm going to draw the cross section of the device, magnify it a little further, and then we will try to understand the charge transport in the channel region. So for VGS, gate to source voltage less than VTH, which is the threshold voltage, there is no channel, there are no mobile charges in the channel, and the transistor is turned off. So there is no current flowing from drain to source region. If we increase VGS beyond VTH, then we will see channel which is formed like what I have shown here in green. The source region will provide electrons, and these electrons will be flooded in the channel. And I'm going to define this particular edge as a reference 0. And let's pick spot in the channel, which is right here. And this is x, distance x from source region. And I'm going to show this small region as dx to show a small piece of the channel, slice of the channel, dx like this. And we go from source to drain, and x will go from 0 to L, channel length L, right here. So the channel charge expression QD is given by width of the channel. Width is in the Z domain here, going inside the screen, width of the transistor multiplied by Cox, which is capacitance of the oxide, multiply that by VGS minus VTH. So VGS represents gate to source voltage. So this kind of makes sense, because if VGS is equal to VTH, then the channel charge would be 0 and there will not be any current flowing. Let's write units here so that we don't make any mistakes. QD is coulomb per meter, and W is width of the transistor, and generally we use micrometer as a unit there, and Cox is cap per unit area, and that is given by femtofarad per micron square. Femto is F15, 10 to the power minus 15 farad. Now as we travel along the channel, look at the dimension x equal to 0, we are at the source, and from x equal to 0 we travel to the drain, x will become equal to L. So Vx at source will be equal to 0, and Vx at drain will be equal to Vds. Important point. So we can write the channel charge QD again as function of x, that will be equal to W Cox, and it would become VGS minus Vx minus VTH.